So we're going to talk about a term called dissociation today. Essentially what this term means is just kind of like a fancy word for a substance that can dissolve. So if you've ever seen something dissolve in solution, sometimes what you'll notice is that if you sit there and watch it long enough, it will just kind of disappear into the solution. And it's not disappearing, it's just that it's separating from the crystal-like structure that you dropped into the water, and it's all getting surrounded by water molecules and taken off individually. So because molecules and atoms and ions are so small, you can't see them with the naked eye, and that's why it kind of looks like it's disappearing. But in a little bit more detail, dissociation is a particular type of compound that we're referring to. So you take a look at the definition up here. What this really means is that we have the separation of ions. We are taking aqueous ionic compounds, and when we drop them into water, because they're aqueous substances, you look in your periodic table on the solubility chart, and you can see, okay, yeah, that substance is soluble in water. That makes it, if you put it in water, aqueous, and it will then undergo this process of what we call dissociation, where it's going to separate the ions that it's made of in the solution. And so the reason that we say it's a separation of ions is because these ions are what make up the ionic compound. Ionic compounds are made of ions, and so it's not that we're making ions in solution, it's just that we're taking a substance that's already made of ions, and we're just breaking it up into its parts, into its ions, and those ions are separated from each other. So if you take a look at these examples that I've got up here on the board, you can see first table salt, which is an ionic compound. If we put it into water, we know it's going to be aqueous. And so when we put it into water, because this is an aqueous ionic compound, it is going to undergo this process of dissociation, in which its ions that it's made of are going to separate from each other. And so you can see this in this little drawing here that I've drawn with just a beaker that's got water in it, and I've got a sodium ion and a chloride ion here. You can also see this for this other example that I've got. It's another type of salt, barium chloride. And I've taken barium chloride. Again, if you look in your periodic table, on your solubility chart in your data booklet, you'll notice that barium chloride is a soluble aqueous ionic compound. And so again, because it fits that description of being aqueous and ionic, when we put it into water, it will dissociate, which just means that this barium chloride ion is going to separate into its ions. Now, something interesting here that I want to point out compared to regular table salt and barium chloride is that sodium chloride contains one sodium and one chloride ion. So when it separates, that's all we're going to get for each sodium chloride molecule, one sodium ion and one chloride ion. For barium chloride, though, you can notice that the molecule is made up of one barium ion and two chloride ions. And so because of that, when we drop it into water, that's what we're going to get in terms of ions in the solution. We're going to get one barium ion and two chloride ions. Okay. These equations down below we'll touch on here in just a second, but the last thing I want to point out is if you come up to an ionic compound and you look in your solubility chart and you notice that ionic compound is not soluble, that means that compound will not be aqueous. And if it's not aqueous, even though it's ionic, if it's not aqueous, it will not undergo dissociation. It will not separate into its ions. And all this means is you're just taking a clump of a substance, an ionic compound that's solid, you put it into water, and that clump's just going to sink to the bottom of the beaker. It's not going to dissolve in the water. And so you may end up, if you drop a whole bunch in, you just end up with a big clump of barium sulfate, for example, in this one, at the bottom of the beaker. If you look in your solubility chart, you'll notice that barium sulfate is not soluble. And because it's not soluble, it's not aqueous, therefore it does not undergo a dissociation. Now, we have equations that we use to depict and explain when a substance is undergoing a dissociation. And these equations are important because it helps us determine concentrations. And we've been learning about concentrations so far in this unit, specifically amount concentrations, and so we're going to look at that as it relates to these dissociation equations as well. So if you take a look at sodium chloride has, if I put it into water, it's going to dissociate. And so I take this substance, I write it as an aqueous compound, and then an arrow, and then I just write it again, but it's separated now into its ions, so I just have sodium ions and chloride ions. Now you'll notice here that if I stick 1 mole of sodium chloride molecules into a beaker that's, say, got 1 liter of water, then what I have here is I've got 1 mole of sodium chloride per liter. And this is just an amount concentration. You remember calculating these in our previous lessons. And so I can just write the concentration here as 1 mole per liter. Now, what we need to understand is we can also determine really easily what the concentrations are of these 2 ions based on this concentration of this substance. So if I have 1 sodium chloride molecule, that's going to give me 1 sodium ion and 1 chloride ion. And so the concentrations here are just going to carry over using these coefficients here. You can see that if I've got 1 molecule or 1 mole or 100 moles, doesn't matter, the ratio carries over. And so the concentration of sodium ions is also going to be 1 mole per liter. And so it is for the chloride ions. The chloride ions are also going to be 1 mole per liter. And so because this molecule was together before, we think of it as one entity. Because these ions are now separate, we have to think of them as separate entities. A really simple analogy that I like to use in classes, I say, if you crack an egg, what you've got is 1 egg. And if you crack it open into a bowl, you're going to now have 1 shell and 1 yolk. And so that's kind of what's happening here is I've got 1 egg and it cracks open into 2 parts, a sodium ion and a chloride ion. They're going to have the same concentration as the sodium chloride here because one of these molecules is going to make one of these ions and one of these ions. If you look at this one right here, this dissociation equation shows that, again, we're doing the same thing, but the interesting thing here is that 1 barium chloride molecule is going to give me 1 barium ion, which isn't so different as over here, but it's also going to give me 2 chloride ions. And so the way that I can write this is I don't normally write it like this, but I wrote it like this to start so that you can see how these match up. But if I have 2 chloride ions over here on the product side, I can just write 2 Cl minus. So instead of doing that, I can just put a 2 here in front. And again, you can see if I stick 1 mole of barium chloride into 1 liter of solution, the concentration is going to be 1 mole per liter. And if that's the case, then the concentration of barium ions is going to be, again, 1 mole per liter. But the concentration of chloride ions is because one of these molecules here makes 2 of these ions over here in solution. Now I've got twice as many chloride ions as I had barium chloride molecules. And so the concentration over here is going to be 2. It's going to be double, 2 moles per liter. And so I can do this with any number. If I had a concentration over here of 0.1 mole per liter, then I can figure out what the concentration is of those ions. And if I had a concentration here of 0.25 moles per liter, I could calculate what the concentrations are of those 2 ions using these dissociation equations. Over here, this doesn't dissociate, therefore I don't write a dissociation equation for those. They're just left as barium sulfate, solid, and that's done. There's no concentrations that I need to calculate because this didn't dissolve in the solution. And that's it. That's what you guys gotta know how to do with dissociations. A little practice question that you can do on your own is first determine whether aluminum sulfate is an aqueous ionic compound. And then if you stick that into water and it has a concentration of 0.3 0.00 moles per liter, what would be the concentrations of the two ions that it produces? Now that we've got a grasp on dissociation and dissociation equations, there's another term that is very similar to it, but there is a slight difference, and we need to know what the difference between them are, and what substances dissociate and what substances do this other thing. And so this term is called ionization. And the ionization is the making of ions in solution. Now these reactions and these, not reactions, but these equations that are up here on the board that I'll write down here in just a minute will look essentially identical to a dissociation equation. But a dissociation equation and an ionization equation are a little bit different in terms of the process in which those ions come to be. So for dissociation, if you can recall previously in the video, we talked that an aqueous ionic compound is a substance that will dissociate. And what it's going to do is it's a compound that's already made of ions, and we're just separating those ions from each other. And then they're just floating around in the solution now. For an ionization occurs for acids only. And what makes acids different from aqueous ionic compounds is that acids are not made of ions. If you remember from the bonding unit, these are covalent bonds. These electrons are being shared. There may be partial negatives and partial positives, but we don't consider those to be ions. These are covalent bonds with shared electrons, and so these atoms that are in these compounds are not ions. Therefore, these compounds are not made of ions. So when we put them into solution, though, what we notice is the end result is the same as a dissociation, and that we get an electrolyte, a solution that contains ions. And so the difference between a dissociation and an ionization is that a dissociation is the separation of ions that compounds are already made out of. And an ionization is the making of ions in solution. So we're taking a compound that's not made of ions, and in the process of this substance being dissolved, electrons are being stripped from one atom to another, and it makes ions out of those substances because those electrons are being stripped from one to the other atom. And so, for example, hydrochloric acid, we put this into solution, and it's going to make hydrogen ions and chloride ions. It's not made of these guys, like sodium chloride is made of sodium ions and chloride ions, but this is the end result of putting this acid into water. Same thing with hydrobromic acid. We get the same substance. Now, when we write these, or we get the same result in terms of making ions. Now, when we write these equations out, though, these equations look exactly the same as dissociation equations. The way that you can differentiate between whether it's a dissociation or an ionization is that ionic aqueous compounds dissociate and acids ionize. And so these reactions here, or these ionization equations can just be written down below. Again, just as before, HCl makes H plus and Cl minus aqueous, and HBr makes H plus and Cl minus. Oops, Br minus. And then if you're given concentrations for these acids, again, you can determine concentrations of the ions in solution as well. And so if this concentration is 0.2 moles per liter, what would be the concentration of those ions? And if this concentration was 0.4, what would be the concentration of those ions? You can do those in your practice booklet and check it with a friend. Another one that you can do is H2SO4. This is also a strong acid that will undergo an ionization. And so what are the ions that are going to be over here? And if the concentration of this acid was 0.150 moles per liter, what would be the concentration of the two ions that it makes in solution? And that's it. That's all you guys need to know about ionization and dissociation. We'll see you in the next video.